This is the demand modeling lecture in our airlines logistics course. Yes, this first slide is again taken from Tobias from TNFL 01. Demand modeling, just as revenue management, is of course part of the economic strategy for the airline. And bringing again this picture from the textbook, demand modeling is mostly part of the strategic phase. So we need to understand how many business, leisure, and other types of passengers will come for each of our flights. So it's not really in the core of the planning phase in which we had most of our attention. It's a more strategic thing. So yes, demand modeling, in order to maximize the revenue, we need to know the demand for our flights, the demand for our services. We need to know how many people want to fly, but also ideally we want to show how many people will, we want to know how many people will not show up for the flights, even though they want to fly. Maybe they bought the tickets, but they didn't make it to the particular flight or whatever. And of course, well, both of these are random variables. We don't know them with certainty. We want to know their distributions. But realistically, we can estimate maybe only the average values of something else. Again, we need to know these things per demand stream or per class in our parlance. And interestingly, that things here do depend on the policy of the airline. We won't go too much into the details on them, but I mean, if we have cancellation fees, no refunds, and other non-popular measures, then maybe, you know, more people will fly in comparison. If you would refund the full ticket, then people would make that decision last minute and not flying. So, and as we spoke in the revenue management lecture, yes, in principle, the price can change with time, but at least some of the airlines, the low costers, have been implemented a simplified fare structure, not all the way to a single fare, but still simple. Any seat goes for the same price, so maybe there are just two classes. Okay, so we want to model somehow how people choose the travel options, or how do they choose the itineraries of flights in the airline industry. Of course, this is a more general question. In any mode of transportation, it's of great interest to understand how many people will want to take one or another, I don't know, public transport route or taxi ride or whatever. And the model that we will look at is reasonably general. So these types of models are seen also in other modes of transportation in other types of demand models. So one important factor is the frequency of flights. And again, I'm not going into too much details on it here, but when I gave a guest lecture in TNFL 01, I don't think it was in your year, we were looking at how the market share of an airline, market share depends on the frequency with which the airline flies between origin and destination. And market share is something that goes between 0 and 1. You can have nothing on the market. Market is a single origin destination. So you can have nothing on this market, or you can have the serve the full market. And you might have seen these so-called S curves that say that, well, essentially, if you match the frequency of, let's say, a single competitor, then you have half and half split of the market. But if you increase your frequency by just a bit, then you can catch, well, that meant to be straight, then you can catch a large proportion of the market. And if you decrease your frequency by just a bit, then you lose a lot of their market share. So that's the reason for all this code sharing and other initiatives when the airlines go into alliances and try to really stay with equal frequencies so that they get equal market share, because any of them is incentivized to unilaterally deviate and slightly increase the frequency and catch a larger market share. And there are lots of questions about how fair it is. forming the alliances and cooperation is good, but colluding is bad. But we don't go into all these economic details. I'm just mentioning here that, well, the more frequently an airline flies on a certain market, the higher market share it gets. But of course, frequency is not the only factor, and in fact, that's important for short flights. Like if there are, Stockholm to Gothenburg, several connections per day, it's important how frequently they fly, so that it's convenient for more people. But for longer flights, when you have connections and longer ways to the airports, frequency is obviously not the only factor deciding the market share and influencing the people's choice. So there are quite a few other factors that do influence passenger choices, and this is a table I took from the book. So the level of service, whether it's a non-stop itinerary or not, and so on, the quality of connection, of course, the price, which here is indicated as so-called fare ratio. So fare ratio is, it's the ratio of the fare to the cheapest fare. So this is something which is larger than 1. Anyway, that's somehow relates to the price of flying. There are many other things. Yes, so the distance or the time, many other factors that influence the passenger's choice, whether the passenger does or does not fly the particular flight. And as in many other cases, when we do modeling, we try to give numbers to everything. And in particular, in this case, we assume that we have a certain set of factors. And capital F will stand for the number of factors. There's nothing to do with the fleet types or fleet assignment, forget about that. And we say that an itinerary is really a vector of length capital F. So for every factor, you have a numerical value. I don't know, if one of your factors is the fare ratio, then you have 1 for the cheapest flight on this origin destination. Maybe you have 2 if the flight is twice as expensive as the cheapest one. I don't know, then for distance ratio, again, you would have 1 for the quickest flight and 1.5 for the flight that takes 1.5 the time, the quickest flight, and so on. So for every factor, we have a number, a numerical value, and the list of such numerical values is an itinerary. This is something that characterizes the itinerary. Okay, that's common model. And again, here is from the book some example of several itineraries. Itinerary what are they called? 1, 2, and 3, whatever between A and B. And the first is a non-stop itinerary, going directly from A to B, and some others. Well, so the non-stop is the shortest one, but it's twice as expensive. So it's 200% the fare ratio, twice as expensive as the cheapest one, whichever is the cheapest. Well, I guess here, this is the kind of base itinerary, and this one has fare ratio 70%. So this is probably cheaper. Yeah, so this is cheaper than this, and so on. So with each of these factors, you have some numerical values associated for all of the itineraries. Not for each, so for some of the itineraries, you have missing values like 0, so whatever. Anyway, again, that's just an example of itineraries and vectors of numbers associated with the different factors that characterize the itineraries. And now we are coming to, I guess, the most slippery part in all modeling, but in particular in, well, modeling the passengers' travel choices. So we assume that there exists some fixed numbers, B1 through BF. And these are the coefficients. And the utility or the happiness of the passenger with a certain itinerary is just a linear combination of these factors. Well, factors now mean as a multipliers. So factor has 2 meanings. One is that, if you have A times B, then each of them is a factor. And also, we were talking about this x's as numbers representing the factors influencing um, the travel choice. So when I'm saying that these numbers B are one per factor, so here I'm saying the factor that influences the travel choice, but in this formula, each of B's is also a factor in the multiplication. So I will try to use the word multiplier when talking about B, and yes, reserving the factor for the factors influencing the travel choice. Anyway, the model says that the passenger's happiness is this sum of products of the values associated with the itinerary, with all the factors, and these multipliers B1 through BF. Okay, so the linear combination. Yeah, that's quite a bold assumption, but that's what linear regression does. It assumes that it's possible to get such a formula. In TNFL 10, I'm also showing this example as for introduction of machine learning techniques, artificial intelligence techniques, neural network techniques, which no longer assume linear dependence, which look at some more complicated dependencies, and maybe that's why they're more successful than the linear models. But anyway, this linear model is one that well, has lived for some time and is still kicking, and it still allows you to play with these values, so they don't have to be exactly the prices or distances or any other quantities associated with the itinerary. They can be some complicated functions of these quantities, and as we will see in an example I will show in this lecture in a minute. Okay, so again from the book, here I guess the same, not the same itinerary. Okay, so they differentiate between the itineraries that fly from east to east and the itineraries that fly east to west, possibly overnight with red eye and so on. And so in this table you have the weights of these multipliers, the BIs for the different factors. So I don't know which one we may look. I mean, okay, let's look at the distance ratio. The factor is negative. I mean, this multiplier is negative because, well, the larger the distance ratio is, the longer you fly, the less happy you are. So it makes sense that it's negative. Yeah, it's different depending on whether you fly, without changing the time zones or with changing the time zones, and so on. So similar, the fare ratio, of course, you have this negative multiplier because the pricier the ticket is, the less desirable, the smaller the utility is. So just some examples from the book. And again, continuing an example from the book, here are some sample values for the itineraries. So this itinerary 1, I'll go back to the previous slide. See if I can do this. Yes. So you look at this number. So we are talking about the itinerary going east to west. So this is the distance ratio multiplier for this itinerary. And now go into the next slide. You again see this multiplier times the value of that factor for the distance ratio. So this was the multiplier, and that itinerary had distance ratio 100 because it was direct, 100%, the shortest one. So, well, you have this term. And then you have another multiplier multiplied by another factor, whatever it is, and so on and so forth. I think this was the price, and this is the multiplier corresponding to the price, and so on. So this is the utility of first itinerary, second itinerary, and other itineraries. Again, just examples, and you can check the text. So just to show you some other examples from other places, I will show you the slides from Mark Hansen and his student. So unfortunately, I no longer have access to the actual slides, so I took them from Google Cache, whatever Google remembers about these slides. But this is about, yes, modeling the demand for the airlines in what they call the duopoly market, market between two, well, an origin destination where two airlines are competing for the passengers. So they were specifically looking at these factors of aircraft size and frequency. So frequency is something that we also at least mentioned. But we will not go into details of these slides, the details of the impact. I will just show you some of the formulas to see how they match those formulas we will add. So let's keep the motivation. I guess we understand why it's important. So yes, this duopoly market. I guess that's just two possible airlines competing. Yes, they have focus on the aircraft side, and so on and so forth. So this is their model for the choice, and they basically start from modeling. So there should be an arrow. So not here. So you start somewhere here, and then you thinking, well, maybe I won't go by the air. And if you do decide to fly, then you have the choice between first airline and second airline. Again, that's pretty standard in demand modeling for any kind of transportation. Do you travel by this mode at all? And then whom do you take in this mode? So this is an important thing. This is really a ratio. This shows the market share. We will arrive at this kind of formula, but this is the kind of formula that gives you this S-shape. It essentially says that the market share is proportional to the exponent of the utility for a particular itinerary, or in this case, a particular airline. So the V is what we call U, the utility of the particular flight. And it's interesting that, yes, your market share doesn't grow linearly with the utility. You know, the larger the utility, the larger your market share is. No, it's proportional to the exponent, and that's the reason for having this S-curve for the market share. So again, that shows up quite often modeling for the airline services. Okay, so here is the thing that I wanted to show in particular, this passenger utility function. So this is the utility. So these alpha, beta, and others are the coefficients or the weights. So these are our B's, B1, the multipliers, B2, and so on. And these are the characteristics of the itinerary. So obviously the attractiveness of the itinerary depends on the fare, depends on the availability, and that's the number of seats. Size is the size of the aircraft, that's a particular thing that they studied, and frequency. So the higher the frequency, the higher is the utility. And the higher the fare, the smaller is the utility. So I think this gamma should be negative. Well, probably it will. But anyway, the general thing that I wanted to see is that, well, they also do this weighted sum of factors. Yeah, there are quite a few ruminations of why they're using the logarithms here, again, not to be linear, and so on and so forth. So this is the main thing I wanted to show you from these slides. There are quite a few other things that just browse through. I guess we will return to it later. Anyway, so this is how the utility of an itinerary is calculated as a weighted sum of the values for several factors. Well, the weight coefficients are these B's. The question is, how do we get these numbers, the coefficients B1 through BF? How do we know what they are? Again, the idea is to do the regression, is to take the historical data and try to find the multipliers, the B's that do the best fit. So how is this done? This is a standard regression problem. You look at the itineraries as points in f-dimensional space. So for instance, if our itinerary has only two characteristics, like this distance ratio, and whatever this thing means, points of sale, weighted city presence, I took it from the textbook. That's how easy it is to get a particular ticket in a particular area in your city. So don't mind what this is exactly. So any itinerary is represented by a point in this two-dimensional space if we have only two factors, two influencing factors. So ease of drawing, we assume that, but there could, in principle, be many more factors. So another itinerary would be another point, and so on. So, okay, so what we do is we gather up a large set of itineraries, and each itinerary is a point in this, well, in our case, two-dimensional space, but also every itinerary has the utility. And assume that we know what the utility of every itinerary is. Well, either you go and do the interviews, or you have some evaluations by thinking, well, if I'm changing certain, quality, certain factor by some number, how many people are getting this ticket, what's their utility, and so on. So one way or another, you gathering data about many itineraries, and every data point lives in this f+1 dimensional space. So f dimensions for the factors, and one dimension, vertical thing, for the utility of this itinerary. And then what you're trying to do is to fit a hyperplane through your points. That is to find these best numbers, the coefficients that best fit your data points. And that's a standard regression problem. You might have seen it in some of the courses. For some reason, it's regression is often taught in courses on statistics, but regression is really part of the linear algebra. It's one of the most important applications of linear algebra. Anyway, if we just look at it in two dimensions, so let's say we have a set of itineraries and they have a single factor that influences. Maybe the price is the one and only influencing factor, so X is the price for the itinerary. And here you have, gathered up a set of itineraries for which you know what their utilities are. So, from different people. So if for this price, the person told you, well, this is my utility. And for this price, another person told you, well, this is my utility, and so on. So for each of these points, you know the price and you know the utility by questioning or otherwise. And you want to find the best line which fits your data points. And a line given by this equation, maybe, maybe the itinerary with zero price has utility 0, so maybe it was the wrong idea to assume that this is price. Maybe it's 1 minus price or something, 1 divided by price, or you're being paid for flying. Anyway, that doesn't matter. So how do you find the best line? Well, you have to define what best means. And in regression, the standard definition of best is minimizing the square error between the actual thing and what is predicted. So this is the actual utility, and this is what is predicted for this value. And this is the error. So you're writing up the sum of square errors and trying to minimize that. And now this thing, the total error, is a function of b. So you write it out as a function of b. How do you minimize a function of a single variable? Well, just as we did with the seat reservation, or maybe you did it otherwise, you take the derivative, and here is your answer. Okay, so that's how you do the regression in the simplest case. So here we had the way to calculate the coefficients in the formula for the itinerary. And knowing these coefficients, and knowing the values for the various factors that define an itinerary, we can calculate the utility for an itinerary. And okay, maybe the utility of a certain itinerary is equal to 3.5 something, whatever. Why do we care about this 3.5? What would be more interesting is to know the probability that a certain itinerary will be booked by a customer. So we need to convert utilities to probabilities. Okay, this is our formula for the utility. So can we just replace U with P and say that, well, this will be our probability for booking a certain itinerary. After all, both utility and probability are some numbers associated with itineraries. And well, the larger the utility, the larger the probability is. But do you see any troubles with doing just that? If you assign, you say, well, this is no longer utility, this is actually probability. So the issue with that is that utilities can be arbitrary numbers, and we saw an example of itinerary that was 3.5 something. The probability cannot be 3.5, it cannot be negative. Probability must be a number between 0 and 1. So how do we convert an arbitrary number to a number between 0 and 1? Well, one possibility is to use the so-called logistic transform. So here is the formula, and here is the graph. You can see that, well, any number, when taken to the logistic transform, becomes a number between 0 and 1. So this function is called the logistic function or the logistic transform. It's also sometimes called the sigmoid curve, although there are several sigmoid curves, several curves that look like sigma or S or whatever. But this is one possible transformation from arbitrary numbers to zeros and ones, and hence from utilities to probabilities. So you can take the logistic transform and get the probability from the utility. And so here I have a short excerpt from the video. I would have shown it in class. I decided to keep the video. I will not show it over Zoom. But this is from the Uber Elevate Summit. Well, you might know what Uber is, this taxi service where people provide services to each other. And Uber Elevate is their branch that is trying to do the air taxiing, urban air mobility, moving people from one places to others, but not with large aircraft, with the small urban air mobility vehicles. Hot topic for research. I will start teaching a course on urban air mobility in this program starting next year. So, well, hot thing. Anyway, the reason I was bringing this particular talk up is that at this time, the Uber Elevate, I forgot who this guy is, but he is talking about modeling the demand, and he mentions the logistic transform or logistic regression. Surprise, surprise. So you can watch him saying that. Okay, so logistic transform is ubiquitous. Another way to arrive at similar formulas for the probabilities of booking different itineraries is to consider differences between people. So we were previously saying, well, here is the itinerary, and you know the coefficients, the B's, so you know the utility of the itinerary. Well, but what is good for one person is not so good for another, and maybe a more realistic model is that the utility is a random variable. Y, again, I'm using Y for a number of business customers, but it has no relation to them anymore. So utility is a random variable, and it consists from two parts. So there is this deterministic utility that we were calculating before, just as a linear regression of the certain factors that characterize the itinerary. Here is this linear combination, plus some random noise. So, different people come and look at the same itinerary and have the same deterministic utility, but this random part is different for different people. And one possible choice for the noise is to say that it is a logistic random variable, or that it is distributed according to the logistic function. Or more specifically, the distribution function, the CDF for the logistic random variable, is the logistic function. So lots and lots of logistics. I have a great excuse to use it here. We are in the logistic program, so it's airline logistics. So we have, logistic algorithms, logistic, all the way. It does show up. So the random variable is called logistic random variable if its distribution function is the logistic function. Okay, so this is the cumulative distribution function for this random variable. Again, cumulative distribution function, just to remind you, is the probability that this random variable is smaller than a certain number. Just again to remind you, distribution functions completely characterize random variables. Knowing a random variable means knowing its distribution function. So if the distribution function is fixed to be logistic, then we have some fixed random variable. That random variable is called, surprise, surprise, logistic. Okay, so the utility now is a random variable, which consists of the deterministic part, common for anybody, plus a random noise. This random noise is different for different people. And now we can estimate the probability of booking the itinerary by saying that, well, a person books the itinerary or buys the ticket if the utility is larger than 0. So this random thing for a random person. If the utility is positive, well, the person is happy about flying this itinerary, then the person will book it. Okay, and what is this probability? Well, the utility y is the sum of the deterministic and the random part. And rearranging the term, this probability is the same as that the random part is larger than a certain number. And our formula for the complement distribution says that this probability is 1 minus the probability that this random variable is smaller than this value. And this is exactly the logistic, well, it's exactly the CDF. In this case, it's a logistic function. So here you go. Here is your probability of booking an itinerary with deterministic utility u. Again, the same thing. It's a logistic function of u, just as we had before, when we just kind of blindly saying, well, let's just convert u to p by using logistic transform. Well, you can also view it as a probability of booking the itinerary, assuming the random noise, which is logistically distributed. Okay, so 2 ways to arrive at the same formula. Here's yet another way. So we can consider a different noise model. So we were looking at the model for the noise when the noise was a logistic random variable. We could say that the utility is again a random variable, and it consists from, again, 2 parts, the deterministic, the same utility as before, plus Gumbel random variable. Okay, and well, any random variable is completely defined by its distribution function. Particularly, the Gumbel random variable has this distribution function. Not go into details of why it is natural or whether it makes sense or not. What is important is that the difference between 2 Gumbel random variables is a logistic random variable. And well, you can prove it by doing the integration. So with this in mind, we may say, well, again, who cares about exact values of these utilities, even if they are non-deterministic, if they are random, or even about random probabilities. What is important is that the customer prefers my itinerary to the itinerary of the competitor. So we consider duopoly market. For starters, let's say just 2 airlines, 2 itineraries competing. And well, I don't care by how much I overcome my competitor. The important thing is that the customer chooses my itinerary. And then again, we can do some maths and estimate the probability that the first itinerary is booked, or the probability that its utility is larger than the utility of the other one. Again, each of the utilities is a random variable consisting of the deterministic part and the random part, deterministic and random. And rearranging the terms here, this is the probability that the difference between random parts is smaller than the difference between the deterministic parts. Now we know that the difference between 2 Gumbels is a logistic random variable, And the probability that logistic random variable is smaller than a certain number is the CDF of that number. And here is the, well, the CDF is a logistic function. Here is what it is. And yeah, rearranging things, multiplying by the exponents. This is the expression for booking itinerary 1. Again, note that it is proportional to the exponent of the utility, not to the utility itself, but to the exponent of the utility. And this is something that we looked also, that we saw also in the slides from Berkeley that I showed you before, which explains the sigmoid curve, the S curve. So if the probability of booking were proportional to the, linearly proportional to the utility, then, well, with the increase in the utility, you would get linear increase in the probability of booking or the market share. So the probability of booking is really your market share. What's the probability that people book your itinerary 1 in comparison to the itinerary of the competitor? And well, the market share exponentially depends on the utility of your itinerary. Okay, so that's again, well, not another way, that's I guess one and only way that we saw how this S curve arrives. Again, very common curve to see in logistics, in business economy in general. So choosing between two itineraries, here are the formulas that we got. The probability of booking is proportional to the exponent of the utility of the itinerary. If we look back at the model that we considered before, which was, the probability of booking an itinerary at all, the probability of flying at all, we had this question, what's the probability that the customer will take my itinerary? No competitors, it's just flying or not flying. Then, well, you may view it, so here is the formula again, so the probability is a logistic function of the utility, and you can rewrite this formula like this, again, by multiplying by the exponent. And essentially what it means is that the probability of booking the itinerary, if it is on one and only itinerary, on the question of whether you will fly, is like, well, it's like comparing the itinerary with utility u to the itinerary with utility 0, because exponent of 0 is equal to 1. So this is really like that first part of the decision tree, whether you fly at all. So this is air travel, and this is not air travel. So this is, deciding between air travel and no air travel. And then within air travel, you can also decide between different itineraries. But this model is very general. You can take care of the whole tree of decisions for the person. Okay, so that was the probability of booking at all. This is the probability of choosing between two itineraries. And we don't do the derivations, but surprise, surprise, the same is true for many itineraries. If you have n itineraries, the probability of booking a certain itinerary is proportional to the exponent of its utility. And that also tells you why it is so important to increase the utility of your itinerary, because a little increase all of a sudden gives you a little increase in utility, all of a sudden gives you a larger increase in the probability of booking, hence market share. And that's why you see all this nitpicking by the airlines. We're adding such and such free, I don't know, SMS or transfer or whatever, and extra T. The more attractive it is, you invest just a little, but all of a sudden you're catching quite a large fraction. Right, so that's the general formula for many itineraries and the market share formula, and then again the link to the slides that we looked at before. Okay, so we know our market share from one model or another. We have increased our utilities and so on and so forth. Still, I mean, we don't know the exact number of people that fly on our aircraft. The demand forecasting is not exact, or at least non-deterministic. Everything is random. Projected number of passengers is random. The interesting thing is that even after you know all the bookings, you still don't know, even for a single fare class like for business passengers, you still don't know how many people will actually fly. And the reason for that is that, well, even after booking the tickets, people may not show here. There are quite a few reasons for why you would miss a connection. And if we had a less technical class, and maybe we would have spent, at least in class, but maybe also over Zoom, collecting opinions of why people would not show up for their flight and what it depends on and so on. Here I'm just listing some of the reasons. What's more important for our technical treatment of no-show is the probabilities of having a certain number of no-shows. So yeah, here is again a figure from a book, and it gives you the distribution, this time the probability mass function of the number of people that do not show up for a certain flight. Okay, so based on mostly historical data, but you can also do a model for that if you want. I don't think they really do models for that, though I don't know much about revenue management in specific airlines. Of course, trying not to tell this information to the outside world, and even when I do get to supervise some phases from revenue management department, when they corrupt the data, or I have to sign some non-disclosure agreement. Anyway, one way or another, in particular from the historical data, the airline can estimate the probability of there being certain number of people who do not fly despite having booked their tickets. Okay, what do you do with the no-shows? Well, just sell extra tickets and anticipate that certain number of people will not show up. And then ideally, if you guessed correctly, then you will fly the full plane, to the full capacity, because maybe you sell 10 extra tickets and 10 people don't show up. Okay, perfect. But still, I mean, you have this interplay. If you overbook too little, then, well, people don't show up and you fly empty seats, you lose profit. If you overbook too many tickets, then you would have to deny boarding to some of the passengers, and you will have to reaccommodate them, get them on another flight, give them compensation, hotels so they have to stay overnight, and so on. And I don't remember if I told you my experience, but I flew some of these small airlines in the US. I haven't seen it really in Europe, and the counter was constantly calling out, "We need volunteers for such and such flight. $200 if you go, I don't know, to Ithaca instead of Troy or something else." It's quite common. I mean, after all, people do have reasons to not fly. And in fact, I heard I heard on the radio that some flying experts would advise, anytime I go anywhere, I just come to the counter and ask, "Do you need volunteers?" And often the airlines do need volunteers. Volunteers are people who go to another flight and then they get some goodies or whatever it's worth. Anyway, you want to overbook, but you don't want to overbook too much. And the last piece in this lecture that I want to show is this model of how we can estimate the optimal number of the tickets, the optimal level of the overbooking. So as before, we will call it X, the number of extra tickets that we sell, the overbooking limit. Y will be the random variable that represents the number of people who do not come to your flight despite having the tickets, so the number of no-shows. So E will stand for the revenue loss, because you fly in empty seats, because too many people didn't show up. And R will be this reaccommodation cost. So if you deny boarding and have to reaccommodate the passenger on a different flight, and give compensation hotel and whatever. So it will be noted by small r. Okay, any questions on this model? I will not go into too many details as we did with the seat reservation, because the idea is that this will be quite similar to the seat reservation, and maybe you have started to see some of the similarities. Well, at least some of the variables are, have the same names, and we will go through the derivations real quick. But in general, it makes sense. I mean, you want to know what your overbooking limit, having some information about how many people will not show up, and knowing your costs for the different actions that you take. Okay, and here is a super heavy math slide again. It's kind of the same. And well, it has the same information for which we spent, I don't know, 10 slides when doing the seat reservation, but everything in a single place. The most important part is the same piece of saturation logic. So if you have sold too many tickets, if you have sold X extra tickets, you overbooked, but fewer than that people didn't show up, then you have to reaccommodate that many people, right? So I can draw a picture. Here is your plane, 100 or whatever the capacity. You sold X tickets extra. So these people don't fit into your plane. And you're hoping that exactly X people will not show up, so you will fly the full plane, but all of a sudden, more than X, Y people didn't show up. So all these people would have to be denied boarding. So now maybe X is 10, you sold 10 tickets, 10 extra tickets. Sorry, I guess I'm doing it in the wrong way. This time Y should be smaller than X, my bad. So you sold, 10 extra tickets, but only 5 people didn't show up. And so for these people you would have to reaccommodate. Okay, sorry. So this is your plane, X is extra, and Y are the people who didn't show up. So X minus Y would have to be reaccommodated. So the formula is correct. Drawing is not the best. Okay. On the other hand, it will make sense to do large drawing. If I sold X extra tickets and a large number of people didn't show up, then all these seats, they fly empty, right? Maybe I sold 10 extra tickets, but 20 people didn't show up. So 10 seats will fly empty. So I will lose E for flying one empty seat, or that much for flying Y minus X empty seats here, Y minus X. And here, this thing is X minus Y. Okay. So yeah, the same logic as with the seat reservation. You either overbooked too much or you under overbooked. Some complicated, I have lost myself, but anyway, with the numbers, this is what it is. Your revenue loss here and your revenue loss here. Okay, so what is your expected revenue loss or expected cost from overbooking X, selling X extra tickets? Well, we find this expected value by conditioning on the number of people that do not show up. And I won't go into all these details, but again, you look at two different cases when Y is smaller than X and when Y is larger than X, and well, regrouping the terms and taking out the constants out of the summation and so on. And then again, using the distribution functions or complement distribution functions for certain things, or probability mass function or probability distribution functions for other things, and again replacing the summation with the integral, saying, well, that this is approximately equal. Here is the formula for your incurred cost. as the function of the overbooking, selling extra tickets. Okay. No need to go into details since they are the same gory details as we have with the seat reservation. Well, when we have the formula, we can differentiate it with respect to x. Again, not going into all the details. You take the derivative of each of the terms, and here is the result. You set the derivative equal to 0, and solve it for x, or at least for f of x, the cumulative distribution function for y. And it gives you the optimal overbooking limit. This is the best x to use in order to minimize the expected cost. Now you can also take the second derivative as we did with the seat reservation to make sure that this is exactly indeed the minimum incurred cost, not the maximum incurred cost. Anyway, this is your answer. So how do you determine such an x? Well, again, you look at the probability mass function and trying to find x such that to the left of x, you have exactly this area of the probability mass function. Here I'm using a picture from the textbook. So if you do look at the textbook, you should be aware of some things at least. So this is where they speak about overbooking. I think they're not taking care of closing the parentheses when needed, I guess here and also here. So there are a few things, as often happens with the book, where you should be careful with things. Yeah, I mean, the area is probability that x is smaller than y. I would rather say that it should be the probability that y is smaller than x, capital Y, the random variable. And why is this y? I think this should be x. Anyway, so with enough care, the book has correct pictures. You follow the book. Hope you will be able to follow that. And in any case, you have in our lectures, hopefully correct. So here is almost the last slide, the summary, the comparison. So this is the overbooking limits, which we just calculated. Here is the optimal limit. And this is the optimal seat reservation for the business passengers, the thing that we studied before and that you have on the homework too, and that we'll have on the exam. Here it is. And you can see that they're kind of similar. So you're trying to find x where the distribution function of y, well, in this case is business passenger, in this case is number of no-shows, is the ratio of two quantities, this quantity and this quantity. Well, here is the ratio of this to this. And again, you can think of them as two reincarnations of the same logic. So if you don't overbook, or if you overbook too little, if you sell too few extra tickets, you will lose E per passenger. And here is your cost, E per passenger. Similarly, with the seat reservation, if you haven't reserved enough seats for the business passengers, then for every business seat that could have gone for capital R, your revenue is only small r. So this is how much you lose per passenger. And this loss is exactly what you have in the numerator here. And yes, on the other hand, coming back to the overbooking, if you overbooked too much, then, well, you would have to reaccommodate people and you lose an R per passenger. And in the denominator here, you have the sum of this cost. Similarly, for the seat reservation, if you reserved too many seats for the business passengers, then, well, you're not selling them to the leisure passengers, and you're losing revenue of R per passenger. And again, if you look at the denominator of this formula, then it's the sum of this and this. So really, these two models for overbooking and for seat reservation are kind of similar, and maybe you can even put them into a common parlance. I didn't want to do that, but the similarities are obvious, both in the statements, if you put them this way, and in the derivations. So my hope is that, well, if you learn one of them, and you should learn this hopefully quite well, at least for homework and for the exam. You will be also able to do the overbooking. We won't have overbooking on the exam, but you will hopefully be able to solve all different kinds of problems with overbooking, just as you should be able to solve all different kinds of problems with seat reservation for business package. Okay, just as a last slide, again, looking at the block scheme of revenue management systems. So our final goal is to understand how many seats we should book for the various classes of passengers. You need the overbooking model for that, and of course you can run the overbooking model separately for the different classes, joint ones, whatever. So this optimization model for the recommended booking limits is something that we looked at in the revenue management lecture. So this is what we looked at just now. The revenue data, well, as I said, we only have this small r and capital R, didn't go too much into that. The forecasting, we looked at it today. Yes, it's often estimated from historical data, but also people do look at the actual booking and adjust the forecasts. Yes, the no-show data and the number of booked tickets go into the overbooking model. So all in all, I hope we have covered everything from these revenue management system or this chart from an idea of revenue management systems. Well, so that ends our revenue management and demand modeling part of the lectures.